Hello, Kirtan, can you hear me?
Yes, sir.
Okay, in the last class, did I give you some problem?
Mm,
Yes, I don't remember about that. Class physics. Oh, okay, okay. We actually discussed in the class itself, right? All right, Kirtan. So look, so far we have talked about EMF, right? Now we are going to discuss about emotional EMF. Okay? Emotional EMF means to say the EMF which is rotating or changing. All right, Kirtan. So we are going to discuss about emotional EMF, right? What does that mean? If you are having some conducting rod or wire um, which cuts magnetic line of force, then some EMF is going to induce. What does this mean by this? If some wire cuts out the magnetic line of force, then some EMF is going to increase. What does this mean here? Look, in general, if you talk about, we know that we have whatever we have seen so far is we have seen if you have loop, okay, if it is moving, it is rotating, you can have some EMF. If some electric field is there because of the change in flux, right? But if I ask you, I have this kind of current, okay? I have this kind of magnetic field, this kind of magnetic fields I have, and out of this magnetic field, if I say this is a rod, let's say this is rod. If I say this rod is okay, right now I don't have any current. Okay, but what if I say this is moving with some velocity v? Okay, and after some time, because it is moving with velocity v, it is going to cover some distance in some time, right? So assume after some time t, it reaches to this position, right? This is the position where it reaches, something like this. So how much time it took? So actually, I don't know what is the time. Assume what is the displacement? You can say x. What is that? Uh, v into t. Okay, this is the displacement. Yeah. What is the x value we have? That is v into t. So this is the displacement value. Makes sense. So can I have magnetic field in this case? Can I have current induced? Yes. How we can have induced current? Look, when we generally talk about the induced current, what is the main crux about it? Let's see. If I say it now, look, one thing you can one idea you can have is, sir, when this was moving from this point to this point, it is in motion. We can assume that this is the area it has swept. We are not talking about what is the area it has. We are I'm right now talking about what is the area it has swept out. So you can say, sir, this is the area it has swept out. This is Okay, yeah. So Kirtana, look, what's happening is here. You can say that, sir, that this rod has swept out some area of this, right? So it seems like that. It seems like that. This has swept out this much area, and I can say that flux passing out is was the flux that you can say that whatever the length was there, yeah, the some maybe this rod is length L, so magnetic field is B, right? What is the new area it has, new flux it have got? You can say initial flux was zero because it was just it didn't move any, but after that it has moved by this. So area you can call this as L into X. So that is the thing. So EMF you are going to get is change in phi by times that is so dlx by t. This is one like one interpretation we can have. Okay, that's how flux is going to generate. But if I ask you, will there be any current? The answer is no, because you don't have multiple rod over here. Okay, you just have a single rod which is moving. So at the end of the day, for a complete current, you need a complete circuit. Here you don't have complete circuit, so it will be only acting as a EMF. EMF in what direction? If you just created a loop like this, because you are increasing the EMF, so increasing the EMF in the downward direction, EMF will be generated such that you have opposing EMF. It means current should flow in this way, but because it's a single wire, you can't have current. It will be having EMF. So EMF will be something like this. Okay, this kind of EMF you are going to have. This is one interpretation which you can think. I can give you another interpretation also. Remove this logic of flux because the rod is very single, right? What you can see, sir, because this is a rod, okay, it is moving. Makes sense. You know, when a rod is moving, what happens over here? I can say there's an electron present here, present here, present here, present here. These electrons are also moving. Makes sense. This really makes sense. If an electron is moving, we know it has some velocity because this rod has some velocity. V in this direction. What is the force? What is the force on this electron? I can just take out this single electron and I will say electron is moving in this direction. Uh, Magnetic field is this way. So what is the force on this? We know this thing. Force on this will be this direction. Makes sense. In general, when we talk about force on the charge, that is QB V, right? So here, because this is the electron, it is negatively charged, so force on this will be opposite side. So you can say final force on this charge is this, right? Can I say that in this neutral charge, in this neutral object, all electrons are getting pushed in the wire itself, they are getting pushed towards this side. So you can think in another way that all the electrons are now pushed in this side. Okay, density in the electron this side has increased, whereas the density of electron has been reduced. So it can also act as a, because this is now negatively charged, so you can say, sir, this is negative charge. This is either it is neutral or positive, you can call it as flow. Can you see we have got the same thing by like both interpretations? Okay, so look, whatever you are doing, you should have a logical answer for that thing. Okay, so think in a deep manner where we can use this way, where we can use this way. It's better to go with a proper concept because if you just remember that loop is there, so in this kind of problem you will fail because you want to be seen in a loop. Okay, so just look at this. Why we even have just a second. When we talk about this kind of situation, just think why we even talking about the loop and all, right? Why we are even talking about the current and all. Assume, Kirtana, if I give you a loop, a complete loop, okay? Here, if I say, sir, if I'm saying this is a complete loop and it is moving inside this, will there be any EMF generated, Kirtana? Tell me first. It's not audible. Hello, Kirtana, can you hear me? Yeah, Kirtana, what do you think? My question is, right now I had a single rod, right? Now I am saying I have a complete loop and it is moving inside this. So what will be the EMF generated? Will there be any EMF or not in the whole loop, in the neck loop? Getna, can you hear me? I don't know why I can't hear you. Yeah, Sweetness, so I have asked some questions. Could you just please answer them? Yeah, Kitna, yeah, I can hear you. So I was saying, in this loop, what will be the next value of current if I take the same loop, put it into this magnetic field, and start moving with some velocity v? What do you think? Kirtana, yeah, what's the answer? What is that no for? Okay, maybe you don't know the answer. Okay. So it's a very big problem. You don't know the answer, right? It's like similar condition I'm giving you over here that this kind of thing is over here, and here I'm asking you what is the current in this loop if I just move this loop with some velocity v. I don't know, like why you're not able to make it. Think of all the concepts you have done so far. Motional EMF is not very big deal. It's a very simple thing. The concepts, only two concepts are required, Lenz's law and Faraday's law. Both things are required for this. Nothing more than this. Okay, all the concepts you have studied so far. I'm not even talking about the first chapter, second chapter, third chapter. The thing which we have done 2 days back, maybe 3 days back, something like that. I'm talking about that thing. What's big deal? What kind of doubt you have created? Please be clear and let me know that thing. I'll take that once and we'll move to the next one. You see, using topics is yeah, okay. Speak up once and let me know the thing clearly. Should I even continue once or we should discuss the previous things again and again? If you want more practice, you can do with that itself. So, I mean, I'm not getting your voice clearly. Yeah, okay. Now, so you're not able to apply the concepts, right? That's the main problem coming out there. Okay, so all right, let's remove this motional unit part. Let's discuss the loop itself. Okay. Assume Kirtana, I'm giving you this kind of loop. Okay. Let's say there's a magnetic field. Wait, there's one thing, like you are not able to apply the concept. So what kind of concepts you are not able to apply? The whole chapter itself, this particular topic, if there's a particular topic that will be much better, right? We can focus on that thing. Few you are able to apply yesterday, but today not, right? Okay, I'll simply ask one question, like, I don't know. Um, okay, one thing. Let me be clear with it. We know that if there's a charge, okay, very simple thing is that if there is a charge moving with some velocity, right? Look, you need to go with a very simple concept, basic concept. If you know the basic concept, you can actually do the thing, right? For example, if I say this is the thing, okay, this is basically a magnetic field. You are having a loop, okay? I'm saying, what is the EMF induced? You know the main concept that for induced EMF, you must be having change in flux, right? Because EMF is basically change in flux by time. If you don't have this, you can't have EMF, right? Just look at this figure out. Even though first of all, right now there is no moving flux. Even though if I make it move, if I make the square out to move, where is going to move? It is still be in the same thing, right? Even if it reaches from here to here, magnetic field is still the same, right? If magnetic field is still the same, flux is still the same, so how EMF is moving? EMF is not generating, right? In other concept, what I just told you with respect to that rod, let's see it that way. How EMF is generated. Look here now. Um, when I said this is a loop, okay, this loop is moving with velocity in magnetic. Makes sense. Each of the wire, assume this is one electron. I'm mentioning wires, electrons, okay? Just assume that each rod contains only single electron. Makes sense. Each of them are moving with velocity v, 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 v. What is the direction of magnetic field inside? So what is the force on them? We know that force will be upside, but right, force will be downside. It means in when you look at this wire, right now this electron is present must be here, so it will actually shift to this side. Okay, this will also get shifted to this side down. What about this charge? In this case, the wire is like this. Okay, it is present here, so it don't have any up and down thing. It can only have left and right, but there's no force in left and right, so the wire will be same. So you can say, sir, the density in this part is very uniform because we are not making any changes, right? So what you can say is what kind of case you can see? It is acting as a two batteries, right? The one battery is this side, positive negative, negative, positive. So what is the net EMF? If you look at this circuit, it is like this kind of condition. It is V. This is also V. So V from this side, V from this side, net voltage is zero. There's no voltage. Understood? You need to go with the concept itself, right? That is zero voltage. We can, okay, so this is one way to get the same thing. Another idea, look, this, why by using this tree you can't get the exact value, but you can get the conceptual, whether the thing will be there, whether what is the force and all direction thing, you can actually get it. If you go with this way, flux change, so if you see carefully, there's no flux change over here, because here also the same field is there, here also the same field is there, still the answer is zero. So both ways are the same. When I took the example of a rod, when I said, okay, there's a rod and it is moving over there in the picture, right? This is it. Yeah. This is a rod. Okay, it is moving with velocity v. So two ways are there. You can. There's a rod moving with velocity v. Electron is present over here. It is moving downside. Force is inside. What is the force on this side? Electron gets shifted to this moment. Right now, what's happening over here? When it reaches by some distance, you can simply say, sir, electron has moved by this margin. So yes, makes sense. What is the electric field value? That will be basically whatever the difference between these two. Basically, what is what it is. If you see carefully, presence of charge at some point, presence of charge some point, when there is an electric field between them. It is a constant like this because there's a charge over here. And there's a charge. All the charges, negative charge, shifted one side because the thing earlier the thing was completely same, right? It had the same as a neutral density. So all the electrons which are shifted from here to here, they must have left some positive charge over here. That forms an EMF. Understood? So it has formed an EMF. Makes sense. Another way to think is, what is that? That way, this loop, okay, that will this thing is actually going to give you some EMF. That is one thing. Okay, this is providing this kind of information. Okay, makes sense. Let's look at this. All right, look at this one. Yeah. So this thing has moved by some margin like this. So what is the EMF generated? EMF is going to generate because you are earlier the length was this, right? When you covered some distance, what is the new area you have got this much? Basically, this is the area you have swept. When you sweep this part, this will increase in the area. So area has swept something. So flux has changed something. If flux has changed something, EMF will be there. The EMF should be induced in a way to decrease it. How you are going to decrease it? By having a current, because rod is this way, so current must be this way to flow. But this is not a complete loop. This is single rod. Right? Initially it was here, it reached here, but you need current in this direction. It's a single loop. You can't have current. That will be magnetic EMF in this. Understood? Same EMF we got by using another concept also. Understood? By simple logic. If you don't know the Faraday's law, I gave you a very simple logic of the previous chapter. I didn't even talk about the Faraday's law when I took this charge wala analogy, right? Very simple, force on a charge. I just took that thing. I didn't talk about Faraday's law. So either way, if you use this concept, if you use Faraday's law, you got the same thing, right? So what's the difficulty to it? Okay, let's do one thing quick now. Example I'm going to give. Assume there's an inside magnetic field. This is a magnetic field direction in the whole plane, okay? Like this. You have a loop, it has some velocity. Actually, it's not in the complete loop. Assume that this is a square. This is an area, and this is a boundary. Okay, in this boundary kit now, after this boundary, you don't have any boundary. You have a loop over here. Okay, it has some velocity v. You need to calculate the EMF value. Understood? When you have to calculate the EMF value, when this thing is completely inside the loop, this magnetic field, when it is completely outside, and what is when it is in the mid state. With respect to mid state, you have to calculate about this length. Assume this is the length L and this is the breadth B. So with respect to this breadth B, you have to calculate magnetic field, EMF. Okay. So how you can calculate it? Look, very clear idea. EMF is nothing but change in flux. By time makes sense. You know that when you are in this side, when you every part of the body is inside, what will be your what I can say? What will okay? Make it into two parts. EMF inside. First EMF inside. When you are inside, what will be the EMF? Flux change is zero, so EMF will be zero. Makes sense. Now the main part is middle. When your condition is like this, so assume that This is the boundary. You must be reaching like this. The moment you cross little bit off, right? So what is this portion? This is x, right? Understood? This is x distance. So you know this x is distance is going to increase from 0 to completely. Mean to say when it was completely like this, the x is 0. When you got it, x has some value. When this it is like this, x has some value. When you completely reach out of this, x will reach to b. Okay. So this x will be going from less than 0 to b. Because the moment this x becomes b greater than b, yeah, when because the moment this x becomes greater than b into something like this, right? That moment the whole thing is obviously change in flux becomes zero. Understood? So this is what we have to think about here. That's how we are supposed to think in this problem. So here if I ask what is a flux? So I said this is a boundary, remembrance. This is a boundary. About this boundary, this is your x. Okay. Let's say I'm taking x from this side. Makes sense. So what is the area? What is the new area you have got? Can I say the new area is this much? Yes. So this area is this much dx and this length is l. So your d phi comes out as what is the flux comes out as? This flux actually came out as something like b magnified as it is l into dx. Okay. What is the EMF? EMF is basically dl dx by dt. Why? Because phi by dt. This is what? What is dx by dt? That is dl. dl. Clear? It means when your loop is coming outside, you can see the flux, this EMF is constant at that moment. Why it is constant? Because when you loop, when you got extra this portion in some time 1 second, because it has same velocity, in another 1 second you are going to get extra this. Mean to say the change in flux is constant. Understood? Because this change in flux is constant over here, you got the EMF constant. Understood this clear now? And EMF outside, completely outside, that will again be zero because you don't have any change. Any doubt till here? If you, just let me know if you really understand this problem, every concept over here. Because if you don't, there's no point on going further with the things.
Yes, sir.
And today also I'm not going to teach any new concept because you're not clear with the previous part. So it's better to discuss a little bit. It is clear, right? Peter, you know one thing, we have derived one formula also. This is a formula in moving EMF. What does this mean? It means that if this is example, okay, concept, motional EMF. This is a formula derivation of motional EMF. Motional EMF. What does this mean? Like, look at this. If you see carefully, in one big wave, now what happens is, assume this is the magnetic field. Okay? So here was a rod. Yes, here was a rod. If it is moving with velocity v, what is the EMF is going to generate? You know, EMF is nothing but d phi by dt. Right? We know this. This is very clear. After some time t, it covers some distance. Right? So what is the area at that time? That is b times of L times of L is total length L times of dx. Right? Sorry, it is x. Makes sense. So yes, that is fine. It has covered any distance that is x. So you are doing d of the whole thing divided by dt. What is that? B L constant dx by dt. What is dx by dt? That is d. So Pietro, this is the formula for EMF generated due to a rod if it is moving inside a magnetic field. Understood? Now, if I go with a previous problem, and can I solve this by using the same concept? Yes. How? Just look at this. Pietro, when I had this kind of loop, okay, leave it. Assume magnetic field is inside, and this is my boundary. Okay, I have this kind of boundary. When my loop was there, when I said the whole loop is moving with velocity v, you know that, okay, one more thing is there, people. The EMF, okay, EMF actually don't have anything. If it is moving in this direction, can I say each part is moving? Look, first of all, this length should be moving. Okay, this length, if it is moving in this direction, there won't be any movement. First of all, that okay. So if this is a rod, it is moving in this direction. What you need to do is you simply take the net length along with that perpendicular distance. That's how you have to get the thing. Okay. At the end of the day, that value is fine. This, if you see that is VLV, right, there should be some length around that thing. So if you see, can I divide this thing into four loops, four different rods? Yes, I can. This is one rod. This is another rod. This is another rod. This is another. If you look at this rod, this is length L. This is length L. This is length B. This is length B. It makes sense. But it is about. Let's talk about this. What is the EMF over here? That is V. What is the length perpendicular to the direction of P? That is L. The complete is perpendicular, right? L into B. This is one, right? Makes sense? Yes. What about this? It also has the same. So you know that for both rod, the direction is same because they are moving in same direction. They have same length and direction. So EMF will be generated in the same way. If it is here, it is also here. If it is here, it is also here. Let's look at the rest, this and this. So you know that EMF is nothing but magnetic field is constant. You need L dot B. Okay. Actually, L cross B. L cross B. Makes sense. Length and this length. Okay. L cross B. Yeah. No, there's a problem with being in this way, analytical investment, you don't need to be technical in okay, let it be, play it. Let's not keep it in a vector form. Yeah. EMF and V should be perpendicular part of it. Basically, you have to take the length component, length perpendicular component. What is the length when you are both are perpendicular? So right now, if you talk about this length, they both are perpendicular. What is the perpendicular component of the rod? That is this part, right? What is the length of this portion? That is zero. They don't have any length. So EMF in this part and this part is zero. So what is the final rod you can see? You can see. At this reason, the final rod comes out is like this. Just look at this piece. The final rod which comes out as is, there is one rod, this connected with this, another rod, this connected. Makes sense. Each of them rod has individual EMF, but the problem is all of them are connected. Because all of them are connected, the net field comes out zero. Because what is the net EMF? That is zero. Around the complete net loop, the net EMF is zero. Because it has same value, it has same value. If current started from this side, current going this side, wait, from here current is also going. It is not possible. Because they have same current only flows from higher to lower potential. This point has same potential, this point has same potential. So why there will be any current? What if this reaches to this position? Assume this is the case when it reaches just like this. Here I don't have any current, but the moment it crosses this. Now click on what happens at this moment. Just it has crossed. Okay, this length is near to zero. Now if you see carefully, if I talk about this rod is moving towards this velocity makes sense. But this side, okay, this is let's say call it this is A, this is B. This is A, this is B. Right now I'm talking about B. What is EMF? That is VLV. But outside there is no magnetic field. So this comes out zero. It means for this loop there won't be any magnetic field. Clear? Basically on this rod the magnetic field is there is no EMF, right? Makes sense. What about this loop? What about this? Because now the condition is like you have this, where this part is in magnetic field, this part is not. You know, if some part is in magnetic field, there will be there will be EMF. And what is the EMF? This value is EMF. We know. So now current will flow. Now your question might be, sir, but in the previous problems which we have solved, my whole loop was a magnetic field. Okay, all the magnetic field was varying, but how I was getting current. Let's look at that. Um, okay, this method is good for your understanding part. Okay, the main method you should always follow. What I can say. This, yeah, the main method basically Faraday's law, then this law. This method is just for your understanding, better understanding. For example, I said this is a loop. Okay, this is kind of loop. So this is if current is growing at this moment, what is the magnetic field over here? So you know, due to this part, magnetic field at this portion is different, and magnetic pole at this portion is different, right? So that's why the EMF generated this side might not be same as this. So that difference can generate magnetic current also. Understood? So you have to be clear with what kind of things are happening in the picture. Is this clear now? I hope so. Um, clear. Kirtna, look, I'm not planning to go with a new topic today. Okay. I will give you one problem maybe. Should I say or not? I don't know. Okay, let's end the session by this itself. Do one thing, Kirtna. Try to solve NCRT problems, okay? Before uh, mutual inductance and self-inductance. Before that part, try it by yourself, okay? Rest I'll take in the next class. I'm not even able to speak, so it's better to end the session by now itself. Tomorrow I won't be sending any PDF because we have not discussed any new topic or something. It was just a problem practice, so you can do it by yourself. So yeah, Kirtan, that's all for today's session. I'm ending the session. Okay? Goodbye. Before that, if you have any doubt, if anything you wanted to ask, you can proceed for that. Okay? Any doubt, please let me know first. Look, Kirtan, you said to me that you don't have doubt, but if you have, please let me know. If you really don't have, do a lot of question practice. Okay, different sets of question practice. Do by yourself. If you're not able to get the answer, go for the solution. If you don't, still you have doubt, send it to Manisha and we can discuss in the class itself. Okay, that is we can actually do because without problem practice you can't solve anything. If you think that just by going with the concepts you will be able to make the problem, no, that won't be possible. Okay? You need problem practice especially because what's the difference between normal board student and JEE student? Normal board students also do the same thing, right? They know every theory much more in detail sometimes, but the problem is kind of problem both are solving. Okay, the only difference in that case. Some concepts are also there, but more in problem practice. So yeah, Kirtan, that's all we will do this. I'll end the session.